All right, hello folks. I am going to go through a little bit of a tutorial on showing you some of the features of the program known as WinCoot. WinCoot, as the name Win implies, runs on Windows-based machines. And this then, therefore, is the machine you need to, the software you'll be using for doing certain applications. And I thought just for fun, I would show you some of these applications because they have great value in your research. And a few of them are probably the reason why you're watching today. So the first thing we need to do is load in our protein of interest. In our case, it's carbonyl reductase. And so you go into, just in case you didn't notice what I did there, you go into File, Open Coordinates. And then you have to know, of course, where you have your stuff hidden. I have one WMA clean, okay? And I will go ahead and open that. And oftentimes you'll see a molecule has a bunch of nomenclature errors and it offers fix them for you. Well, yeah, I just hit yes, fix them. Why not? Nomenclature is just, essentially it is nothing more than us trying to name things. So one of the things I'm going to have you do is overlay your inhibitor molecule, whichever one you're trying to model, into the active site of the enzyme. And the way that you go about that is quite simple. First, what I want you to do is you'll use this display manager and you will click right here and it shows C alphas plus ligands. And when I do that, you'll see that everything except the C alpha and, by the way, the ligands that are bound here, okay? And so what I'm going to do is you'll note that some of these things are fading in and out and cutting in and out. There's a way to fix that. So I'm going to make it so that the depth of view going into the Z-axis, into the screen, is going to be, I guess if you look at here, that would be the X-axis, because here are your axes that are here. So that would be your X-axis going into the screen if you were to go by that. But in terms of here's your Y, X, and then going into the screen would be Z. So that's how I was categorizing it. But this shows the axes for the actual molecule. Now, all I do is I go into Draw, and I go down to Clipping. And clipping's the thing that helps us see what the depth is into the screen. And if I slide that all the way over to the left, you can see a lot of the molecule just popped up. Now, that's probably a feature that isn't shown in the tutorial that I have made for you for docking ibuprofen into cyclooxygenase, but it is one of those other extra things that are pretty useful to know about. Now, so what I have here is what you probably are noticing, hopefully, is that first of all, just like in the tutorial, if I want to center on an atom, I put my cursor over it and then I push down on my scroll button on my mouse. And now I have centered that in the screen. So I do like that feature and wish that something like that actually was present for VMD, but it's not. So anyway, this is AB3. This is a molecule of inhibitor for AB3. And then the other molecule that is here that's also important is NADPH. NADPH is here. Now, the cool part is since I selected this ligand, you can see over in the left corner what the structure is. And if I wanted to center on, say, this NADPH, now there's my structure for NADPH. So if you center on on one of the small ligands that are bound to the protein, then that's what you will find. Okay, so now presumably you have some kind of an inhibitor that you're going to want to overlay on this structure. Now, this structure right here, here's an oxygen, here's a carbon. So that's a CO. So if I go back to Display Manager now, and I just turn on all of the side chains so you can see the protein itself. I'm not sure why maybe it's already open, that's why. Where's my Display Manager? Oh, I already, okay. If I just go bonds by color, then what happens is you can see right here is oxygen is red, and then these yellow color, gold color compounds, atoms are carbons here. And then right here, I guess what would you call it? A yellow, straw yellow color. Then these blues are all the nitrogen. So in this inhibitor AB3, which was actually, it is the inhibitor that was solved. The structure has been solved. And so its position isn't one that was modeled in. What they did was when they created the crystal, that they collected the data to form this crystal structure and determine it. They also soaked in the inhibitor and it bound. And this is where it binds, which is where we would expect it to bind. There are, some other key things here, like here's the catalytic tyrosine that's close to that. So what we want to do is use this as kind of like an overlay. The assumption is other inhibitors will bind in the same spot. So you can use that as a beginning point, which is what we're going to do. So I'm going to make this, I got to find, so here's an inhibitor 10B12. I'm not sure if this is the one where I say, okay, here's 10B12. So 10B12 is way out here. It's nowhere near where it needs to be. So when you load in your inhibitor, chances are the one you're going to dock, it's going to wind up distant from our protein. And remember, we're looking to overlay it on AB3. So it's kind of hard to see where AB3 is. So initially, I recommend, again, going to Display Manager, which I already have open, and go back. So this one is bonds colored by atom, and this one is CAs plus ligands. And so you can see where my ligand is. It's over here. I'll zero it in on it. So I'll center it in on it. And the idea here is I'm going to want to move this so that one of these here, you can barely see it, but here's a carbon oxygen bond. So that carbon oxygen bond here or here, I'm going to try to align it on this carbon oxygen bond if possible to begin with. So the beginning stages, and it's just like doing what you did for the ibuprofen, is you go into calculate, model fit, refine. And then there's this thing called rotate, translate, zone. This is where you can click and drag. I'll show you. Double click on the molecule you want to move once you click that. So that's the one. Now I can move this molecule where I need to move it. And I got to just move some of this stuff out of my way. I keep running into difficulty. Here we go. All right. So I want to move these windows out of the way, and I'm going to move this guy to where I'm hoping, again, I want to put it. So, and then you kind of rotate around, and actually I got lucky there. Now, I'm not going to do all the moving, and I'm not going to do it, but you can fine tune it and move it around. And then you can also do rotation with these sliders. You see how I do that? You can rotate in the different angles, and that's what you have to kind of do if you want to. A lot of the fine tuning is going to be involved there. You can fine tune the translate. This is what your mouse is doing. It's these sliders will move it in the different directions, and you can do that with your mouse as well. So let's just say I like this. Is this a good one? Well, here's the next thing you're going to have to do. So whenever you get it kind of where you want to put it, you hit OK here, and it will save the molecule to the new coordinates. So I've done that. See, now I can already tell this is a bad alignment because just seeing without any side chains, look how close I am to the C alpha. So obviously this has to swing out somehow, but I'm not going to worry about that right now. I'm going to go ahead and turn back on my display manager and turn back on all of these color by atom. And now here's where it gets pretty crazy. So here's where you're going to want to bring things in. And so this is what we were trying to overlay on, which is great. And then you're going to want to look at all the different places where this could be aligned, and look for close contacts. Like this is too close to the NADPH. I can tell it's too close, but we can make measurements, and you can make measures here just like you can in VMD. And so you go to distances and angles under measures, and you measure distance. And so I can click on the things I want to measure the distance from, and you can see that's 0.63 angstroms is really too close. Honestly, something like this where you have a carbon which isn't very polar at all with a polar carbonyl, I would say that should be more like over 3 angstroms, probably, maybe 3.3, 3.4 at the closest. And so what I usually tell students is find every place that's within 3 angstroms and find out how close they are. They should never be closer than 2.5 angstroms from any of the amino acids. Now, the one to not worry about is AB3, because here's the idea. AB3 is just a template. When we actually do the final touches on the modeling, we will remove AB3 and just this guy. So you can ignore all of the AB3, this here AB3 atoms. So you don't have to worry about those being too close to here, because remember, you're trying to overlay. And so so you have a couple of options. When it comes to NADPH, you're kind of stuck. So you're going to have to just move this guy, swing it out of the way. Now, there may be times, though, when you're going to be bumping into amino acids too closely. And in those cases, you'll probably want to, you can move the side chain of the amino acid. And that is another thing you can do in WinCoot that isn't so easy to do in VMD. So this is why we're using WinCoot. So I'm going to go ahead and swing this guy out here somehow. So let's see if I can do it. So I have to hit rotate translate zone again, double click on the molecule I want to move, and then I'm going to try to do some rotation. Oh, that's not the rotation I want. I actually have it pinned down exactly where I don't want it to be pinned down. So I'm going to have to do this. Which is crazy, but it's what I have to do. See, what I had to do is flip it around so it can get kind of nutty. And so I'm trying to get this worked in over here, remember. And this is the tricky part. See how I have to keep maneuvering this to try to make it and I'll hit OK just because it gets confusing otherwise. So I hit OK and it's there. So I hit OK and you can see now I moved this guy out of the way. And by doing all that little maneuvering, actually, I might have moved everything pretty well out of the way. But oh, gee, look at this. This methionine 141 is always going to be in the way, and it may be possible that you have to move it in order to free up some space, because look how close it is. It's way too close to this ring. Now, I still would only move side chains at the very end when you're convinced you have moved this and minimized as many unfavorable interactions. Usually they're too close. And so don't go moving side chains, okay? First move this as much as you can, get it in a clean spot, but I'm just using this now as a means to get you to hopefully I'm going to try rotate translate real quick here again as a means to get the rotation. I'm just checking a few things here. So I'm moving this again, trying to see if I can make it so I'm not so close to other amino acids. And look, this whole piece got all whacked out. Now it's bumping into that. So you can see this can be very tedious. And so we got to just keep moving things around until we can find, that. So I can already see it. Here's that tryptophan. So, I got all these places I got to move this around. And I'm kind of moving it the wrong way now that I see that. I guess I want to move these things out. See how easy you can get all messed up. It's pretty easy to do, actually. So I'm trying to picture how to manipulate this so that I can get it where I want it, which is non-trivial, to tell you the truth. I'll just hit OK for now. So now we got this in this new position, which isn't a very good position at all. But let's pretend I've done everything and I'm like, oh boy, this tryptophan now is just in the way. I can't really move this any other place. It's great in all these other spots, so I don't have to keep moving amino acid this anymore. If I could just move that tryptophan. So what I like to do is I'll center on the thing I want to move. So you can see that's a really close contact. And we can see, can I move this and maybe have to remove this a little bit? Here's how you move a side chain. So the key is you use this thing called rotamers. And so there's a thing called the rotamer tool. This is auto fit rotamer. We don't want that. This is rotamer. So you click rotamer, not the green one, but this one. And I click on it, and then I double click on the molecule the amino acid I want to pick a rotamer. Now rotamers show you can see here's a rotamer where you can move the side chain according to these rotamers. And these are like, they look at all the different angles that this thing can move and the degrees of freedom it can have. And you select one of these rotamers because these are what's going to be naturally occurring. And you try to find one that's swung out of the way. So I'll move that one. That one's probably a little better, but still a little close. Let's see if there's a better one. No, that's not better. There we go. Look at that. I swung that out of the way, except look what it did. It bounces right into the side chain and backbone of the protein. So that's not a good choice, even though it did swing out of the way here. So this is where the rotamer will be if I hit OK. Let's try this one. Where's this? Oh, that's worse. Oh, let's see. Ooh, there's a possibility there. That's probably too close right there, but maybe we can pick a rotamer for this one. But let's try the last rotamer and see if it's better. No, that's worse. So probably, let's see. This one is not great because it's too close over here. But you get the picture when you find the one you like that isn't making bad connections, but that's far enough away. Like look, it's looping. That's not going to be a good one. And you just keep spinning around until you find the one that's going to be, see, that's still colliding with our inhibitor. And you just keep spinning around until you find. So this one may be our best bet. So I'll hit OK. So you can see now I have moved the positioning of our guy. But now let's see if we can find a rotamer. This one, there might be a rotamer that I could use for this threonine. We'll see. There's only a couple of choices, but maybe I can swing one of these out of the way. Ooh. See? That may be the ticket. Do you see how I did that? And I was able to move that. Now, if first of all, let's say I love this, which I don't, but let's say I did. Let's say you got to the end point, you're like, okay, it's positioned where, after talking with Henry, I know where he thought this certain things I should be trying to do. Great, I did it. I feel happy. I want to save my inhibitor. And because I changed the side chains, I also have to save the new version of this protein. So you have to go to save. And you go to open coordinates, not open coordinates. What did I just say? You go all the way to save coordinates, sorry. Okay. And the first one that's up is our protein. So I'm going to hit select file name because I want to save our protein. And instead of calling it clean one, I can just say, tryptophan, TRP, or W is also tryptophan. I can go W 229, and I can't remember what threonine it was, but threonine, and you'd give it its numbers, whatever it is, moved. So you remember what it is, you changed on it. So I would save that. And that saves the coordinates, and pay attention to where it's saved. I saved it in the WinCoot folder. You may have another folder. Now, I'm not done though, because I've saved the coordinates of the protein and all the new positionings that I have. I did not save the coordinates for this guy, okay? And so, oh, I forgot to tell you, when you're doing the saving of coordinates, when you do rotamers, if you do a rotamer, okay, I'm going to double click on this one again. It tells you which you'll click until you find the rotamer that matches up. Okay, so this is this one. So I would write this information, the one that you felt was best, write down which rotamer it is. It's rotamer 6, P90, 6%, chi/1 equals 60. Write that whole amount there. That way you know which rotamer you have. And write that in your notebook. And then when you save it, when you save coordinates, put down what the file name is and also where you saved it. So keep track in your notebook, that kind of stuff. You should have your notebook out, writing notes down as you go on how you did this, okay? All your steps. It is research. It does belong in a notebook, and some kind of notes on what you're doing. It turns out to be important. So you can kind of think of this like an experiment. Now I go in and I need to save coordinates again, but I don't want, I've already saved this one. See, it's got the new name and everything. I'm going to save now this one. And so I notice what I did. I clicked there and I saved my inhibitor. Now I moved the X, Y, and Z coordinates of my inhibitor in order to do this docking. So I hit select file name, and maybe you can give it 10B12 position 1 or whatever. You give it a name, and you might try a couple of different positions as you do this. And in your notebook, you would write, okay, I saved it as 10B12 position 1. That pairs with protein 1WMA, and give whatever that name is. It you know, which ones you moved and all that kind of stuff, so that you know, okay, this one goes with the protein where I had to move the certain side chains, and that way you explain in your notebook which one of these goes with the corresponding protein. And that turns out to be really important, because if you don't do that, it's not going to be easy to find out how to use your work. Now, if you don't want to save in WinCoot, you can always save somewhere else, and here's where you would select where that is. But saving to the WinCoot folder is as easy as anything, so I'll just do that. Okay, so that's how I save everything. Then you can bring it back up. Once you do all this, you can bring it back up into WinCoot, sorry, VMD, where you get the pretty pictures, and you can look and take measurements and just take a better look at it. Make sure you like the fit. And when you do that, you'll see that I've provided you 1WMA clean, no AB3. Now, reason why, if you remember, if you move your amino acids around, you're going to want to do that first thing. You'll want to create a version of this in WinCoot. So you'd have to open this one up in WinCoot, and then select the rotamers that you change, so that you can create a form of the protein that has no AB3. Because then when you open up AB3, you can, this one, so I'll open this one up here. Okay. So this one has no AB3 in it. And yet I can then, and here's where I got to remember how to find my WinCoot. Here, I'll go File, New Molecule. So I'm in VMD main. I go to Browse. And here's where I think it's under Document. Nope. Okay. I think it's WinCoot right here. So it's under Local C, WinCoot. And you can see I saved my different groups here. And so here's my position 1. I can open that up, hit load. And so now you can see, here's where everything is. And I got no AB3. So now you can say, and remember, I didn't open up the one where I moved this tryptophan, so it's still in the bad spot. So you'd have to go back and VMD, create a new version of this protein where this one's moved, and the threonines moved that I moved before. So anyway, that's kind of what you'll be doing. And then you can go through and start making measurements and say, okay, how close is this carbon to that? And you'll identify all the places that things are really close. Now, one thing I want to mention, and not knowing if you've had biochemistry yet, or if I've told you this yet, but when these types of structures are solved, we use X-ray crystallography a lot of times. And X-ray crystallography, that is a technique that shoots X-ray beams at crystals that are well-formed, hopefully. And those well-formed crystals will, the electron densities around the atoms will diffract the X-ray beams, and then through a series of mathematical procedures, you can calculate back to the positions of those atoms that diffracted the different beams. Now, the problem with that is hydrogens, the whites here are hydrogens. These were calculated in when I did an energy minimization of this molecule. Hydrogens do not show up typically in X-ray crystal structures. And so none of these are showing the hydrogens. So you got to fill them in your head, remembering that, you know, a carbon, you have to know the structures of the amino acids. So, you know, oh yeah, this is a phenyl ring that has resonance, you know, conjugated double bonds around here. And so you got to remember where the double bonds are and stuff. And then you can count the hydrogens off the carbons, because, you know, every carbon has 4 hydrogens. But when we make our measurements, we don't measure from the hydrogen. Okay. We measure from the atom that's attached to the hydrogen to the other atoms. And that's where I give you try to make it so that if something can hydrogen bond, in other words, got the right kind of hydrogen and the right kind of hydrogen acceptor, in other words, fluorine, oxygen, nitrogen, if it can hydrogen bond like that, then you would expect a range of distance between, say, at the very closest, maybe 2.6 angstroms. That's pretty close. And out to about 3.1 angstroms. And you really don't, you know, that range is reserved pretty much for hydrogen bonds, I would say. And maybe if you had a salt bridge, like ionic kind of negative charge, positive charge interaction, you might be able to get that close. Outside of that, everything else should be beyond 3 angstroms. And so if you have things that are falling between under 3 angstroms, they better be in a very favorable type of interaction, such as a hydrogen bond or that kind of thing. Otherwise, you should probably seek to have them a little further out than where they are. So those are the tight spots that you'll have to look for. Another cute little trick I use using VMD to help me notice if I have, it's just a quick view. It's not the best way. I still think measuring all the distances, everything that's close, and making sure nothing's too close. The other way I do that, and it does work out pretty good, and I'll show you this way. It's just a quick and dirty sort of way of seeing things. I'll go into my graphic representations, and I use this trick here where, okay, so I'll put this like in licorice. So this is my inhibitor, and I like to thin it out. You can thin things out. I just think it looks better that way. And then I'll go and switch to my protein, and I'll pick that and surf. Okay. And this only works if you're using, hold on a minute. This only works if you're using, hold on a minute. There we go. There's surf. This only works if you're using the clean, no AB3, this trick. Otherwise, it won't show up right. So here we go. Now I'm going to show you this. So if you look, here's our inhibitor, and every place our inhibitor runs into, you know, this area where it runs into the surface of the protein, that's an indication that this is not bound very well at all. And there you can see it's poking through into the middle. So obviously this is maybe not your best arrangement. And so we'll have to tweak this some more and figure it out. But remember, I was just doing a quick and dirty. I didn't expect to get this to look very good. I do get them to look pretty good though. And so if you look here, you'll be able to see where things look bad. Now, if you're this bad, you probably didn't do anything right to begin with. So you'll want, like, when everything looks good, all of these things that you're seeing poking through and into, see here, they should be nicely nestled and resting on top here. and not sticking into the different areas. So that's the trick I use when I do this. So anyway, that's kind of a long drawn out thing, how to use VMD and WinCoot to do docking of the different inhibitors that we have for carbonyl reductase. So hopefully that is clear to you, and this video will have been useful.